Good day, guys. We're going to start another integration technique today that will be new for you, but the origins of it is not new. This method we call integration by parts is designed to reverse derivatives that are gotten by the product rule. So that's actually where we're going to start today, is to review the product rule for derivatives and to build in no other words, a formula that we use to solve an integral that we call using integration by parts. So let's get started. Let's start by stating the product rule for the product of two functions. Now, instead of calling them f of x and g of x, just to make it easier to write, let's just call them u and v. And so we're going to start with function u, function v, and we're going to multiply them together and make the product uv. And now we're going to take the derivative. And this is our standard product rule. So I'm going to write derivative of uv. And on the other side, we have our typical, what we know as the product rule. The first function u times the derivative of the second function v, dv, plus the second function v times the derivative of the first function, or du. And we often refer to this as the rhyming scheme 1 d2 plus 2 d1. But now we're going to take the integral or antiderivative of both sides of this equation. And so I'm going to put now an integration symbol in front of every term of our previous equation. But the only integral that can be simplified is the first one, because it is strictly a derivative followed by an antiderivative. And so the left side reverts back to the product uv. On the other side, we cannot work these integrals directly because it's the integral of one function u and a different function's derivative in both of them. But what I am going to do is rearrange this equation so that one of these integrals is all by itself, and that's going to be the one in the middle. So think about subtracting the integral of v du to the other side, and I'm going to write the middle integral by itself, and then rearrange the other side like this. And this is what I'm going to highlight. And just what this points out is that I have an integrand on the left that is a product of one function u, but a different function's derivative. And on the other side, we have an expression for how that integral could also be represented. If I knew function u, because it was given in the original integral, and I could figure out what dv was the derivative of, and that would be v, it's going to go here and here, and the derivative of my original function u appears in this integral. Essentially, what this equation is stating is that this first integral can be expressed in terms of a different integral, and what we're hoping for is that the integral v du is one that we will be able to solve with the techniques you've already learned. A couple examples will help, I think, solidify what we're going to attempt to do here. But essentially, integration by parts, the key is to identify the parts. And typically, the integrands of these integrals are products of two expressions or two functions. One of them you want to think of as the function u. The other one you want to think of it as the derivative of some other function v. All right. So here are three classic examples. All of these integrals are only solvable using the method of integration by parts. None of these integrals you could solve at the moment with any other technique you've learned up to this point. Notice these are all products of two distinct expressions, like the function x times the natural log of x, the function x squared times the function e to the x, or the function e to the x times the function the sine of x. Okay. Throughout the next couple of days where we work on integration by parts, you will learn how to solve all three of those. Okay, now let me write our little formula again underneath the title here, and we'll kind of read the guidelines together, these basic guidelines together here. remember, the original problem you're going to be given is assumed to be the integral on the left side of this equation. And so we have to identify what part of the integrand do we want to assign the name u, and what part we want to assign the name derivative of v. So here are two basic guidelines. One guideline suggests how we might pick the dv part. The other guideline suggests how we might choose the u part. And usually these guidelines kind of work in conjunction with each other. So the first guideline says, pick for the dv portion the most complex part that will fit a basic integration formula. Here's why, because whatever I assign to be dv, or derivative of v, I would have to know its antiderivative, because the antiderivative of dv is v, and it occurs here and here. So whatever I pick for dv, or derivative of v, I'm going to have to know its antiderivative just right off the top. Whatever I pick for u, its derivative has to go in the other integral. Okay, so that kind of leads to guideline number 2. Since we would like this integral here to be simpler than the first one, it says try picking for u something whose derivative is simpler than u. Okay, here's a very common one. Commonly, we will pick u to be the power function x to the n, simply because the derivative is 1 degree smaller, you know, with the power rule. Okay, so I'm just going to write u equals x to the n is often a good choice. There's a couple exceptions to this rule, but it's pretty common that if I have a power function like x squared multiplying by something else, there's a pretty good chance I'm going to pick x squared or x cubed as the u, because its derivative gets 1 degree smaller. Now, in number 1, we're choosing dv. Now, things I could not pick for dv would be things like the natural logarithm function, because even though we know the natural log's derivative, we don't know its antiderivative. So pretty much anything else that we typically come across, we know its antiderivative, but we want to pick the most complex part to be that. I think you'll see after a couple examples what we're going for. Okay, so the first one we're going to try is a product x e to the x. I'm just going to highlight with my pen the two factors. Okay, and I'm going to write the formula down again just to remind us how we're trying to see it. So remember, in the original expression, one of the two factors, you're going to give the name u, function u, and then once we do that, to fill in the other side, we're going to have to know its derivative here. The other factor, we're going to pick dv, and whatever I pick for dv, that's the derivative of some other function v. Its antiderivative has to go 2 different places. Okay? I like to organize myself by making a little four cell table here. The left-hand side, I'm going to be concentrating on what's function u, and then what's function u's derivative, because both of those things appear on the right side of the equal sign. And then on the right side, I'm focusing on what is function v and what is function v's derivative. Now I'm going to put a star on the two parts that come from the original integrand, u and dv. Okay, so the other two parts have to be calculated by us, hopefully quickly. So remember, the guideline said pick something for dv that you know the antiderivative of, and try and pick the most complicated part you can find whose antiderivative you would know. Now, x and e to the x both have pretty easy antiderivatives, but typically e to the x would be considered more complex. And also, the second guideline says pick something for u whose derivative is simpler than u. Well, in this case, if u is the factor x, its derivative is simply 1, and that's for sure simpler. and the derivative, and if e to the x is dv, v would also be e to the x. So now I'm going to try and fill in my formula by writing the original integral again. And remember, this is now u dv. Okay, so now over here on the right, we want to fill in u times v. So according to my table, that's x times e to the x. And for this first time around, I'm going to write the names under there again. Minus the integral of v times du. Well, v is e to the x now, and du is just simply 1 dx. So one way you know this is going to work right is if the integral you have yet to solve is one you now know how to solve easily. And that's what we've got now. So my right-hand side is now going to be x e to the x again. Now I will just work out the integral of e to the x, and it is e to the x. And now my right-hand side is completely solved. Don't forget the constant. And I can now complete this equation. That the integral of x times e to the x is x e to the x minus e to the x plus c. I encourage you to check this answer by just working out the derivative of the right side. Now remember, the product rule is going to be right there. But notice that that is true. The derivative of what we ended up with is in fact back to x e to the x. So we know this is right. One more for today, and that is this one here. Now, we have the two factors, x squared and the natural log of x. And I'm only going to put in the parts that come from the original integrand first in my chart this time. And I'm going to write the formula down one more time, just so it helps me remember it. Integral of u dv is equal to u times v minus the integral of v du. So in the original integrand, we have to pick something and call it u and something and call it dv. Now, a little thought this time. The last example, we picked the power function x to the first to be u. And that might be something you would think about again. And then that would mean the dv is the natural log of x. But that is a bit of a problem because even though we know the derivative of the natural log function, to complete this table, we would have to know the antiderivative of the natural log function. And we do not know that. That integral is the one we haven't studied. In fact, later in this lesson, we will solve the integral of the natural log of x because that integral requires the integration by parts method. So this approach here is not going to go anywhere because we don't know what the log of x is the derivative of. Okay, it would be wrong to put 1 over x up here because that's the derivative of the log x. It's not the antiderivative. So what we're going to do is just going to switch places here. We are going to put the logarithm function, call it u, and we're going to call x squared dx the dv part. That way, this kind of satisfies both guidelines. Remember, it says pick something for dv whose antiderivative follows a basic integration rule. This definitely does, because the antiderivative of x squared is 1/3 x cubed. And then pick something for u whose derivative is simpler. Well, I guess because the derivative is now just 1 over x, that's considered simpler than the natural log function. Let's see where this leads us here. So we're going to write the integral x squared ln x dx. Now that's technically v and then or dv and u here. Okay. But anyway, the right side is now supposed to be u times v, and so that's uv multiplying across the top, and I'm going to put the 1/3 x cubed in the front of it. 1/3 x cubed ln x minus, another integral. This time the integrand is v times du. I would prefer just to multiply that on the side and just put the simplest answer here. I would encourage you to think about what do you get when you multiply 1/3 x cubed times 1 over x before I write it in there. So I noticed that x to the third times 1 over x would result in x squared. So what I really have is 1/3 x squared as my integral. See, now what I mean again is the integral we have left to solve is going to fit a basic integration rule. This only requires the power rule now. So I'll be able to finish this off here, rewriting the uv again. And now this integral only requires the power rule. I'm going to make it x cubed, but then divide by 3. So it's really 1/9 x cubed. And then we are done. So the final equation is the integral of x squared times the natural log x dx is equal to 1/3 x cubed ln x minus 1/9 x cubed plus c. I hope this will help you get started. We will see you back next time for a couple other examples and a couple more advanced problems that you can solve with integration by parts. We'll see you back here soon.